Okay, I will present some progress of computation of new Neutron Monitor yield function and some applications. So, brief outline, some background. I will speak about atmospheric shore, Neutron Monitor, altitude surveys, and Monte Carlos, and I will focus the application and about the analysis of this amazing event of GOE 74. So I can skip this because we can use neutron monitors to reveal the spectra of nearly relativistic and relativistic SCPs and to study other transients as Forbushes and Acres. Roughly, we can distinguish, impulsive and gradual events. And here it deserves to mention that when we are dealing with very impulsive events, as in the profile, in the, let's say, in the particle counter, as a neutron monitor, you can reduce the time resolution up to 1 minute. This is relatively reasonable for neutron monitors, but it would result in let's say, very fluctuated count rate increases between the stations and eventually would lead to reduced precision if on your reconstructed spectra. And here, it's according to our experience, it depends on the events, but usually we are taking 5-minute integrated data. So what's the physics basis? When we have a particle, let's say an SCP, which is entering in the atmosphere. It is producing a shower of particles, which is raining down to the ground and eventually can be registered by a neutron monitor. And because all the stations are inside the geomagnetosphere, this means that every station is sensitive to the given direction of arrival of the SCPs, that is the asymptotic direction, and for given energy range. This means that we can use the global neutron monitor network as a giant spectrometer, which simultaneously accounts the anisotropy and the spectra of the arriving particles, and within their evolution throughout a given event. What's happening? Okay, so what's okay, okay. What's a neutron monitor? So the core, it's a proportional counter. When we have a secondary neutron from the cosmic rays, there is a neutron capture by enriched to boron 10 nuclei, and which in practice immediately decay to alpha and lithium. Both of them have almost equal ionization capability. These counters are surrounded by a moderator, so it provides, it should increase the probability of an absorption inside the counter of the secondary neutron. Usually, we are using paraffin or nowadays a polyethylene because it's the energy loss per elastic collision, it's increasing with decreasing the atomic mass, so we need some materials with high concentration of hydrogen. The second component, this is the lead producer. It serves to increase artificially the statistics by N to 2N or 3N reactions. For this purpose, we need a large nuclei, which is, let's say, white lead with reduced cross-section for neutron capture. And the fourth component is the so-called reflector. This is the it's made with the same material like the moderator. The aim is to avoid registration of the thermoneutrons which are produced in the detector surroundings. So here is a summary of 2 generations of neutron monitors. In my knowledge, there are only 2 IGY monitors still in operation, one in Jungfraujoch and one in Poch. Nowadays, it's in practice is the standard monitor, the NM64, or the so-called super monitor. There is around 50 stations in the world. And there is not exactly a 3rd generation, but there are several stations which are operating the mini neutron monitor. So smaller tubes, but with increased density of boron trifluoride inside. And there are several stations which are operating now. So in order to relate somehow the primary practical characteristics with the counts, it's a it's known expression. So the count rate, it's integral product of the GCR or SCP spectrum, accounting the modulation, the yield function, and the geomagnetospheric transmissivity. If we have a good model and account properly the transmissivity, we can integrate this expression over the cutoff rigidity of the station. And let's say if we have calibrated or well measured a spectrum and yield function, we can account the modulation or vice versa. And here I will not speak about the latitude surveys, but this is one possibility. This is just to place a monitor in a I took the Polar Stern because it's a very nice icebreaker. It's a nice picture. And to scan through all the rigidity and to measure the count rate variation of the neutron monitor, so-called the latitude survey. And with convenient parameterization, here is an example of the Dorman function. We can assess and obtain the parameters of your response function. However, this function, it's I'm not recommending to use for ground level enhancement analysis. First, it is obtained against galactic cosmic rays, and we know the SCPs, they're processing different spectra. So that if you are taking the Dorman function and perform certain analysis, so it can be very accurate, at least according to my experience. So it is just a parameterization of latitude survey using the Dorman function, and right hand panel you can see the different response of LED-free monitor, so without LED, and comparing with the standard one. So the LED-free monitors, and specifically those that are located in a high mountain altitude, like the South Pole and Dempsey stations, they are more sensitive in the low energy range, so that to the SCPs. The other possibilities is to make a full Monte Carlo simulation in both atmospheric cascade and on the detector efficiency itself. And here you can see a 6-tube monitor, and the beam hitting one of the central detectors. And you can see that there is some impact on the neighbor detectors. This means that 3 single tubes that are separated in some large distance are less effective of 3 tubes that are together. And the pioneering simulations were performed some 25 years ago by Clement Dorman. And here it's just, you can see the registration efficiency on the left panel. against neutrons and protons for a standard monitor, and on the right panel, compared with some measurements performed by Shibata-san using an accelerator beam. So once we have the Monte Carlo simulations of the shower and the particle registration itself, you can compute your yield function of the monitor. And the long-standing, and it was unsolved problem, was the disagreement between the watt-heated surveys. Here are the dots and the stars for different watt-heated surveys versus the several yield functions, the Clem-Dorman, the Flukiger, Hermann de Brunner, and Harmorau. And in our group some 10 years ago, we considered a typical shower effect and introduce some geometrical correction. And you can see that this new generation of health function is in perfect agreement with the watt-heated survey. So an additional calibration was performed against the Pamela and AMS measurements with this yield function, considering several neutron monitors and for different modulation potentials. And it's also compared with Caballero, Lopez, and Morale function, and the Manjar, which is another function based on Monte Carlo simulations. And you can see that the Oulu function is which much better agreement and comparing to the others. The second improve after this improvement, we also compute the yield function for isotropic incidence for different levels, ranging from 500 grams up to sea level, so that we can model the neutron monitor with each neutron monitor in the network with its own function, which is corresponding exactly to the altitude of the station. And in addition, we provide a parameterization of these curves. And the last improvement, it's in the frame of this project and in this deliverable. It was based on a study by John Clem, which point out that the contribution of the oblique events, not only arriving from vertical incidence, can be important specifically for very anisotropic events or very complicated, or according to our experience with count rate increase above 100%. And here you can see the yield function for different incidents, 0, 15, 40, 45 degrees, for sea level 70, 700 and 500 grams. The next is work in progress. As already said, there is a mini neutron monitor, and here we compute the registration efficiency and for the standard and mini neutron monitor, and also compared with Shibata-san. And we have that, you can see that there is some good agreement for the NM64 and with Shibata-san previous computations. And now we have the compute registration efficiency for the mini neutron monitor. And we are working on this geometric correction effect for mini neutron monitor, because the dimensions, it would be different to the standard one. And we will provide at the end of maybe this year the updated yield function for mini neutron monitor. And it is maybe next step, if we have enough time, to provide the same result for EGY, so that it would be possible to analyze historical events. So how can use the yield function? So the convolution of the yield function, so it's okay, it's no pointer. So the convolution of the yield function with the spectrum is giving the counts. So the ratio of the contribution of the SCPs, accounting the angular distribution and magnetospheric transmissivity over the background due to the galactic cosmic rays can give the model of the expected counts. As I already said, we should account the magnetospheric effects. So the first step is the computation of the asymptotic viewing directions and cutoff rigidities of each station. We are using a new open source updated magnetospheric tool, which use combination of IGRF and one of the Tsiganenko models. And as I already said, for the complicated events, we are accounting 14 different segments of the asymptotic directions. However, it can be largely simplified if we take just isotropic Kelp function and particles with vertical incidence with a convenient initial guess and by minimization of the difference between the measured and modeled count rate increases, we are able to reconstruct the energy spectrum, anisotropy axis direction, and pitch angle distribution. So in our model, we can assume different type of spectra, just several examples. Either a modified or exponential or Ellison-Ramati can be assumed, or a band function. Usually, we are making the fit of the angular distribution using a Gaussian fit, and even in the simplest case, we have about 5 unknown parameters, and in the most complicated case, up to 14 unknown parameters, which means that we need about 30 stations to have a good convergence. And let's move to the example. We know that our sun was very active about a year ago, and there was several X flares were popped out within a week and a few days. And on 10-11 of May, there was a sympathetic eruption of two regions, which accelerated particles observed by GOES. And you can also observe by Neutron Monitors. This event was observed during the recovery phase of a very deep Ford-Bush decrease and giant geomagnetic storm. So this was a very complicated interplay between the reduced geomagnetic cutoff of the stations, the SCP signal itself, and Ford-Bush decrease recovery. Here just to see some of the interplanetary conditions, and the DST was about minus 400. I'm skipping this simulation. This gives actually the necessary information to choose the fit of you will see the sun and anti-sun direction. According to our simulations, here you can see the reduce of the cutoff rigidity, specifically in the mid-latitude stations. And we are computing the real contribution of the SCPs, and for the analysis, we consider only the polar stations, whilst all the other stations were assumed with new count rate increase. Those are the asymptotic directions for selected stations. So the the maximum would be expected at Jumbo, Dom C, and the South Pole, which is actually the case. So according to our analysis, the best fit was achieved using modified power law rigidity spectrum with moderate hardness and notable roll-off. And most interestingly and importantly, the best fit is by double Gaussian, so particles arriving from sun and also some contribution from anti-sun direction. Verification of the anisotropy axis position was performed by Bayesian method. So this is a counterput of the minimum residual of the fit, where the cross is the direction of the interplanetary magnetic field. And okay, it's my conclusion. Using a new generation of verified neutron monitor health function, we are giving a first walk spectra and angular distribution during GOE 74. And this event can be considered as a stress test of our current instrumentarium, which is pretty old. Those are tools for tooth extraction from the beginning of the previous century. So at least some of other instrumentarium is dated about 50 years. And even more the Levenberg Marquardt and Reach regression. And for this particular event, the analysis was very similar to a tooth extraction. Okay, thank you.